This is a Geiger counter kit from MightyOhm that I modified to operate off 5 volts and to display the data on a I2C LCD screen. Hi, I'm Alex doing Alex Things, and in this video I'm going to show you the modifications that I made and where I got the ideas from. Now, keep in mind, I'm not a professional, just a hobbyist, but this video should give you a great starting point for any projects that you want to do with one of these kits. Of course, when I first went to look up how to do this, I went straight to Google, and I ended up at this site called MightyOhm Forums. And this is all the way back from 2013, but people were wondering how to communicate with the Uno R3 directly. This guy, Jeff, I believe he is the creator of this little kit. He says that there's 2 ways to do it. One is to connect the pulse output of the Geiger counter directly to the Arduino and count pulses. The other is to connect the serial port of the Geiger counter to the Arduino RX-TX lines. But in both those cases, you're going to need to level shift from the 3 volts up to 5 volts for the Arduino. I didn't have a level shifter, and if you keep reading, Tony, give him credit, he put up this post, and this is pretty much the modifications that I've made. I had to tweak his code a little bit simply because he has a LCD screen that's just a regular liquid crystal that has the parallel input, but I've got the I2C enabled LCD, so I had to tweak this a little bit, but I'll go through all that. Anyway, there's only 2 real hardware modifications you actually need to make. You're just changing 2 resistors. Here is the MightyOhm Geiger counter kit after you build it. I just put tape over the Geiger tube so I don't accidentally hit it. So to change this to work from the 3 volts to 5 volts for the Arduino, we're going to need to change R6 right here. That's currently 330 ohms. We're going to need to change that to 1000 ohms. Then we're going to need to change R11, which is currently 100 ohms, and we're going to need to change that to 330 ohms. Okay, R6 is now 1000 ohms, and R11 is now 330 ohms. Okay, since I realized that we're going to be powering this with the Arduino, I no longer need the battery holder. These tubes are polarized, so just remember to keep positive lined up with positive. These tubes in here, apparently they can get crushed, so I'm going to do that very carefully. I've got it hooked up, and now let's go ahead and apply power. And looks like it's working. Got a check source I can grab. This is pretty neat too. This is my CDV 700 that I restored. Maybe I'll do a video on this too, but it's got handy dandy check source on it. Alright, so it's working. Let me pull the power off so I can show you this. So it seems a little counterintuitive, at least it did for me, but the pulse section here, which is called J6. Okay, so the pulse, which is this part here, right here. I don't know if you can see that, but these are actually labeled which pins these are. 1, 2, and 3. The one with the arrow, that's going to be normally 3 volts, but since we've modified it with those resistors, this is where we feed in our positive 5 volts. This is going to be our pulse output. So to power it, you don't hook anything up to that middle one. And then the one furthest to the edge of the board, pin 3 on J6, that's going to be your ground. So if I disconnect it from here, just so you can visually see this, power feeds in on the left here where the arrow is on J6, and then ground is on the right, the closest to the edge of the board. Now what I'm going to do is I'm going to go ahead and hook up my oscilloscope probe to the middle. Okay, so here is the oscilloscope view of the output of that middle pin on the J6 section. And I hope you can see these pulses right here. I have my scope set to 0.2 volts per division, but I have the times 10 set on the actual scope probe. So let me turn the light on so you can see the graticles. So we've got 2, 4, 5 volts. So we're at right about 5 volts right here, which is where we should be now that we're running off a 5 volt power supply. Now the pulse duration in the instructions when you're building this kit, it says that it's a very short 100 microsecond pulse. My scope is currently set to 0.5 milliseconds per division. So one of these boxes on the x-axis is going to be 0.5 milliseconds. So each one of these little ticks should be 0.1 milliseconds because there's 5 of them. So these pulses look like they're about that distance, about one of the, let me grab a pencil, about one of these right here, which corresponds to 0.1 milliseconds or 100 microseconds, which matches up with what it should be. Now that we've confirmed it runs properly with the 5 volt power supply, we can hook it up to the Arduino and make sure it's going to run off the Arduino's 5 volt power supply. Let's plug that in. Alright, seems to be running. To wire this up, we've got the Arduino Uno, the I2C LCD screen, and the Geiger counter board. The Arduino 5 volts is going to go to both the LCD screen, VCC, and the Geiger counter J6 pin 1, so it's the one with the little arrow. Arduino ground is going to go to both the LCD screen ground and the Geiger counter ground, which is pin 3, the furthest one away from that little arrow. To connect to the LCD screen for I2C, we're going to do pin A4 to SDA on the LCD screen. Then the Uno pin A5 to the SCL line on the LCD screen. Then the Arduino pin D10, the digital pin 10, that's going to go to the GC pin. So I was going to take the output from here, but after doing some more reading on the Arduino forums, I think it's better to take it from the serial, because if you do it here, you're going to have to count pulses. And personally, I think with the code that's posted, it's easier to do it using this. So again, the numbering's the same as like on the J6. So this is 1, 2, 3, 4, 5. So you want to take the output from pin 5 of the Geiger counter. And that's again going to pin D10 on the Arduino Uno. So that's how you wire this up. So again, power, positive 5 volts goes in where the arrow is on pin 1 on J6. Your ground is going to pin 3 on J6. We're taking our output from the serial section, J7, pin 5. So again, that's 1, 2, 3, 4, 5. The breadboard just helps me get the power connections there. For I2C LCD screen, the blue one is the serial clock line, white one is the serial data line, red is VCC, and black is ground. and the Arduino. The serial output from the Geiger counter board is going to pin 10 on the digital section. And then the I2C, of course, you've got your A4 for your serial data line and your A5 for your serial clock line. Now that we're all wired up, let's go take a look at the code. We'll get that figured out, and then we'll come back to this, upload it, and power it up. Here is the code. I put this link here where you can get the original code. I'm just going to scroll through it so you guys can see it, and then I'll go through and I'll talk about everything. This part here, I included this so you can see on the serial monitor what's going on. And this is if you want to omit the counts per second. All right, so now we're going to switch to the other code. So here's the fully annotated version with all the comments to help explain everything. First thing you're going to want to do is include the LCD I2C library. This one, if you don't have it already, you're going to have to download it. And then we're going to include the software serial library. Then your software serial, you're going to set that up. We're calling my serial, and the only pin you need to connect to is pin 10 because we're only receiving from the MightyOhm. Set up your liquid crystal I2C display with the address, 16 characters, 2 lines. Then this is a message buffer. It's designed to hold up to 64 characters, and it's going to be set as a char. Then we're going to define a variable for a string of characters. I think it's called a char array. I'm not a programmer, so just keep in mind this is my best interpretation of what's happening in this code here. Okay, then we're going to do a int comma locations, and we're going to set that to 6, and I'll show you the reason for that. The MightyOhm outputs a comma separated value list, so it's going to be in this general form here. I just highlighted where the comments are, so you've got 1, 2, 3, 4, 5, 6. So we have 6 commas, and then we also have a slow, fast, and instant indicator. Only one of these will show at any time, but all these are basically defines the sampling and averaging period used by the MightyOhm. So the standard sample period is a 60-second long period, and that's called slow. If the counts exceed a certain threshold, it switches to a fast mode, and fast mode simply has a 5-second sample period. And if the counts per second is greater than 255, it's going to move to instant mode, which is simply counts per second times 60. That's all if you hear me talk about S, F, and I indicators, that's all that is. It's just the MightyOhm board indicating what sampling and averaging period it's using. Okay, but that's why we have 6 commas, right? Because there are 6 commas in the CSV. Now in the setup, we're going to start the serial at 9600. This code does use the serial monitor, so you do want to include it. Then you're going to start the software serial at 9600. Initialize the LCD, turn on the backlight, set the cursor to 0, 0. You don't have to do this part. The Geiger counter, print on line 1 and then start up on line 2, delay for 2 seconds. But you do want to clear the LCD. And that's the only time LCD clear appears on here. If you overuse LCD clear, it causes the screen to kind of flash, and that's not very desirable. Okay, for the loop, we're going to test if serial is available, if the software serial is available, and you do want to test this because there might not be any new characters. And if there is a characters available, we're going to do myserial.readbytesuntil. And if you look here, it has a car terminator, which is this in, I think it's called a null or a new line. It's got a buffer, so this is what read bytes until, whatever read bytes until reads off of myserial, it's going to be stored in read buffer. And then we have the size, which we are setting to 64. Just like up here, read buffer set to 64. Now we're going to set the variable read string equal to read buffer. So whatever read bytes until just read, read buffer, that's going to, that's what read string is going to become. Then we're going to find comma locations, and just, no, it's down here, but we're going to call that function to find the comma locations, and we're going to call a function to print to the LCD, then we're going to call a function to print to the serial monitor. For find comma locations, this function simply separates out the data from the serial output, and we're introducing a function called index of, and it gives the ability to search for the first instance of a particular character or string within a string. Remember, the MightyOhm gives a CSV output, and I rewrote it here just so it's clear. And remember, read string is whatever read buffer is. So this is the first comma right here. Comma locations 0 equals read string index of. Now remember, index of, it has two components, as you can see when you hold over it. It's got the parameters. So the first part of it is the value that you're searching for, and then the second part of it is where you start your search from. Now, because we're looking for the first comma location, which is going to be this one right here after CPS, we don't have to start our search from anywhere because we're starting from the beginning. So we're just starting right here, boom, there's your first comma, and that is your first comma location. Now for your second comma, we're going to do comma locations 1 equals read string index of, we're searching for the comma. This second comma right here has nothing to do with the index, that's just telling us now we're into the from part of this. So from comma location 0, so from the first comma, plus 1. So from this first comma, plus 1, now we're at this space right here before the numbers. That's saying search for a comma from, these windows, search for a comma from the first space after that first comma. So now it's going to look, and boom, there's our second comma. So that's our second comma. Yep. See here, I wrote this out, so if what I'm saying isn't making sense, then it's easier to just read it. It's right here. Now for the third comma, comma locations 2 equals read string index of, search for the comma. Again, this comma has nothing to do with the index, that's just separating out the index from where we're starting our search from. We're going to start our search from comma location 1, which is this whole thing here. So we're going to start our search from the second comma, but we're going to add a space. So from the second comma space, now we start our search from here. We go all the way past CPM, and here is our third comma. So that's how you find the third comma, and it just repeats over and over until we get to the sixth comma. I won't go through the other ones because I'm sure you get the picture by now. But that's how that works. That's how we separate out the comma locations. Now the next thing that's going to be called is print to LCD. Here's that function here. Actually, let me scroll up so you can see this too. So for print to LCD, now we're going to use something called dot substring, and this allows you to look for an instance of a particular substring within a string. A substring with two parameters looks for a given substring from the first parameter to the second parameter. The parameters here are commas. So now we have I think it's called a local variable. We're calling it line 1. So string of line 1 equals CPS colon. That's all line 1 equals right now. Now we have this I think it's called a compound operator. Oh, here it is. Compound assignment operator. All this plus equals means is the variable, in this case, it's going to be line 1 equals line 1 plus something. So what it's going to be is it's going to be line 1 equals CPS colon plus this stuff. Now with substring, you can see here begin and end index. So we're going to define where we're going to be searching within the string. So we're going to search from the first comma, right, because that's right here. So the first comma plus 2. So first comma plus 1 plus 2. So we're going to start at the number. Tony's original code had plus 1, and what that did is you started here at the space, and then you would have the space end up on the LCD screen. Just to save characters, I'm having it start at the actual number, so there will not be a space between the CPS colon and the first number. Anyway, that's kind of besides the point. But so we're searching from the first comma plus 2. There's our number, to the second comma. So just basically these numbers here. Okay, so now line 1 equals, well, it's a variable plus, so it's going to be line 1. We add on to that a space. So all the previous stuff, a space, and then CPM colon. Oh, I could just write that here. Yeah, so line 1 equals all the previous stuff plus CPM. Now we're going to read the data for CPM. So we're going to do line 1 equals all the previous stuff plus we're going to do substring, and we're going to search from the third comma location plus 2 to the fourth comma location. So we're going to search from the third comma location, so 1, 2, 3, plus 2. So here's a space, and there's the first number. So we're going to search from there to the fourth comma. So these numbers here, which correspond to the counts per minute. Okay, then we're going to do line 1 equals everything previous plus 4 spaces. And I believe this just simply has to do with making sure that if you have really high counts per minute, it clears the remaining character spaces on the LCD screen. This is kind of how you would clear spaces without using that LCD clear that you don't want to use a lot of. So that's everything for line 1. Now we're going to set the cursor on the LCD screen to 0, 0, and we're going to go ahead and print line 1. Line 1's now done, and now we're going to do line 2. So again, we're creating a local variable. I'm pretty sure that's what this is, a string, line 2, and that's going to equal microsieverts per hour colon. So now line 2 equals microsieverts per hour plus all the stuff that read string substring is going to read from the fifth comma plus 2 spaces to the sixth comma. So we're going to do the fifth comma, 1, 2, 3, 4, 5, plus 1, 2. So we start here at the number for microsieverts per hour, and then we're going to read all the way to the sixth comma right here. So that's all the numbers that are possible for the microsieverts per hour. So we read that. And now line 2 is equal to all that previous microsieverts per hour in the data, plus these 3 spaces here, 1, 2, 3. Now we're going to do the readString.substring. So we got to set where it's going to be looking for in that string, and it's going to be from the sixth comma, this one here, plus 1 to the sixth comma plus 3. So we're at plus 1, 2, 3. So it's only going to read, oh wow, I didn't realize it would highlight every single S. It's only going to read this S right here. Now if it was in fast mode, instead of slow being here, fast would be here, so it would just read an F. And if we were in instant mode, INST would be here, and you just read an I. Then we're going to set the cursor to the first space on line 2 of the LCD, and we're going to go ahead and print line 2, that variable that now contains all this stuff. I hope that was pretty clear. It took me quite a while to put a lot of this stuff together, a lot of trial and error. And then for the serial monitor, I just basically followed the example of print to LCD, this here. And then I just did string. I did CPS, CPM, just meaning counts per second, counts per minute. And just, I mean, if you tracked what was going on here with string line 1 and string line 2, this will make sense. Okay, I'll scroll through this again real slow, or slow-ish. All right, let's go ahead and upload this. Okay, so now we're uploaded. You can see down here in the serial monitor all the counts per second, counts per minute, microsieverts per hour, and the mode that we're in. I'm going to go ahead and take a lantern mantle and put it over the tube. And I'm going to silence that because it drives me crazy. So now you can see we're in fast mode. And you can see on the serial port there how everything shifts to the right because, you know, the digits are increasing. And that's what runs you out of room on the LCD screen, which is why in the code I omitted those spaces after CPS and CPM for the LCD screen. These spaces are here on the serial monitor because you have plenty of room. Okay, I'm going to pull the mantle off. And you can see now we're back to slow mode. And the counts per minute and the microsieverts per hour are going to stay a little elevated simply because we're in slow mode. It takes about a minute for all the readings to settle back out. So I hope that made sense to you. I'm going to switch now to showing the overview of the project so you can see what this looks like on the LCD screen. And I will try to post these in the description or in a comment, so it's a lot easier. You can just copy paste everything into your Arduino IDE. Here we are, all uploaded and powered up just using a 9-volt power supply. As you can see, there's no space between the counts per second or the counts per minute, which leaves us some more room in case the values get higher. You can see so that's line 1, and then you can see line 2 has printed out the microsieverts per hour at currently 0.07, 0.06, and you can see the slow fast indicator right here. I'm going to go ahead and put the lantern mantle back on the tube so you can see how the screen responds. And I'm going to mute it. You can see the slow fast indicator already fell off because the microsieverts per hour went to double digits. And you can see how quickly the counts per minute, we start to get close to the edge of the screen. If you had a space between counts per second and counts per minute, you'd already have that, 3,000 and whatever fallen off already, and you'd only have, you'd only be reading 3 digits there. All right, I'll take it off. Wait for it to settle out. And now you can't see it, but we are in slow mode because our counts per second is low. So this does take a while to settle out. And now you can see we're in slow mode. And we have settled out back to what typical background is at around 20-22 counts per minute. I'll put the codes in the description or comments below. I might create another video about this project as I continue to complete it. If you have any questions, feel free to ask in the comments. I hope you enjoyed this video. If it helped, please like, and if you want to see more of this, go ahead and subscribe. As always, may the Lord bless you and keep you. May the Lord make his face to shine upon you and be gracious to you. May the Lord lift up his countenance upon you and grant you peace. By the power of the Prince of Peace, Yeshua. Amen. See you guys. Shalom.